Hi everyone, welcome to our QCAA QCE Year 12 Chemistry revision. I'm not going to use slides for this. I will provide loads of materials for everybody, but I will just use my whiteboard and my voice. We'll start with units 1 and 2. If you're watching the recording, you might be taking a break, but quick break. Units 3 and 4. And then maybe an hour and 15 minutes answering some practice exams. We know roughly what's going to be in the exam, but we know a bit more than most people. Let's get some inside sources. So we're going to focus it based on what has been said, what's been in the practice exams that have been given to the students, and what the examiners have told us. So we'll start with unit 1. So I always say with chemistry, if you understand the periodic table, you understand everything about chemistry. And this rings true for all of chemistry, organic chemistry, biochemistry, physical chemistry, whatever. So the periodic table is made up of groups that run down, and these groups denote the number of valence electrons. So when you get to organic chemistry, you don't know the number of valence electrons, then you're going to struggle big time. We also have periods, which run acrossways. Now these tell us the number of electron shells. Why is this important? Well, we need to know how to build our electron configurations, our Lewis dot structures. So we need to know the number of valence electrons and number of electron shells. It's also important for bonding. On the left-hand side of the periodic table, we have the metals. Metals form, these different colored whiteboard marker. Metals form positively charged cations. Again, why is this important? Well, we need to know how to, when we're building organic compounds, and when we're doing our Lewis dot structures, when we're doing the naming of compounds, we need to know the charge on the metals, and then we have on the other side, we have the non-metals. So these are, generally speaking, negative charge. So again, why is this important? The big thing with this exam is going to be redox reaction reductions, specifically the electrochemical cells. If you don't understand this, then you won't understand the signing of oxidation states, which will tell you what is oxidized, what's reduced, which then can allow you to build a balanced redox reaction. What else? So if I get rid of this, we have, try not to go too far. I'm guilty of going too quickly if you're writing notes. So if we're looking at the groups, 1, 2, so we don't take into consideration the transition metals. We are looking at group 1, group 2, groups 13, 14, 15, 16, 17, 18. We have the noble gases. So we're not worried about those. They don't really react. You just need to know that they are perfectly stable. We have the groups. So group 1 metals will form +1 cation when they bond with a non-metal. Group 2, group 3 plus 3 plus 4, usually plus 2, 4, or 6, depending on what they're bound to. Carbon is usually 2 or 4, sulfur is normally 6. So we now switch back. So now we have -3. This is generally speaking. So if we were looking at naming the compounds, so if we have sodium and chlorine, would combine to create Na. So when they are by themselves, they do not have a charge. Their oxidation state is 0. When they bind together, we know that the methyls donate their, in this case, their 1 electron to the non-metal. So in this case, sodium has a charge of +1, chlorine has a charge of -1. The takeaway here is the charges have to balance when we're naming. So if I had H2O, oxygen is in group 6, so it is -2. So in order to balance those charges, we have to have 2 hydrogen. So that will make it +2. Some other things to note with the periodic table. And again, this is everything about organic chemistry is based on this electronegativity. So electronegativity refers to 2 things: the reactiveness. We have francium down the bottom left, which does not react, it's the least reactive. Then we have fluorine at the top of the halogens in group 7. So what this line means is that across the periodic table and up the periodic table, you will have increasing electronegativity. Now, what this also means, and we can tie this into, just skipping ahead a little bit, but trying to keep everything together. So let's look at the one that gets everyone, polarity. So not only does electronegativity refer to the reactivity of a molecule, we then have tendency when 2 molecules react with each other. Will one of those atoms hog the shared electrons in a covalent bond? I spent an hour with a student yesterday doing this, and it is a really simple way to start. In your final exam data package that you get given the electronegativity values. So if we have something like hydrogen and carbon, so hydrogen being group 1, so H plus H and C. So if you look at the electronegativity difference between carbon and hydrogen, the difference is only 0.1. And I'll come back to this when we look at bonding in more detail, but the electronegativity difference is only 0.4. If you take carbon and oxygen, the difference is 0.8. I'll just clear. So, and if you're currently doing a Year 12 exam or Year 12 study exam, study 4 exams even, you'll know that what we have here is we have a hydrocarbon, the basis of organic chemistry. They are non-polar bonds. I'm not going to go any deeper than naming it as non-polar or polar. If that electronegativity difference is greater than 0.5, the compound has a covalent bond. Now we know if it's between a non-metal and a metal, like NaCl, it is a ionic bond or anionic bond. So these are covalent. So classic exam question for Year 12 chemistry and first year uni as well is here's 3 compounds. Is it an ionic bond, a polar, or a non-polar, or what they call a true covalent bond? Just look at what's in it. Hydrogen and carbon. Go to your table at the back of your book that you've been given, the data package, whatever they call it now. And if the difference between the two is less than 0.5, it's non-polar. If the difference is between 0.8, if the difference is higher than 0.5, such in the case of carbon to oxygen, we have 0.8, which makes it a polar bond. If it's between a metal and a non-metal, it's an ionic bond. We also have metallic bonding, but they don't seem to be testing that, so we won't go through. A little bit on modeling the atom. We have the nucleus in the middle. We have positively charged protons. Neutrons that don't have a charge. Then on the outside, we've got electrons. Now, we should have all known that from grade 9, grade 8. And what we are going to go through is these different levels. So we have level 1. Level 2. Level 3, level 4, level 5, level up to level 6. So level 1 is the lowest energy level. Level 2 is the second highest. Level 3, level 4, level 5, level 6, level 7. What happens is it's not a 1 electron per shell. If we look at it like this, this is the first level. Within that level, it contains this suborbital. So we have the orbital, just hearing massive thunderclaps. So disappear, you know why. So orbital, then we have, so this would be denoted by 1. Suborbital, which is denoted by, in this case, S, P, or D. For year 12 chemistry, you don't go above element number 20. So you don't go above the 4s shell. So let's start with the basic one. Hydrogen. Has one, we know hydrogen, I'm going to teach you how to use the periodic table to your advantage. So hydrogen is period 1, group 1. We know it has 1 electron in 1 electron shell. So it's going to be in orbital 1, suborbital s, and there's going to be 1 electron in that suborbital. 2 seconds. So if we go to helium, which is the next one, we have 1, it's in group 1, period 1, so we have 1 shell, s orbital that has 2 valence electrons inside it. We can also draw a box. So we put the first electron in, and the other one spinning the other way. If we look, we go to the next, I'm only going to go up to a couple because it's read on relatively quickly. If we looked at lithium, so lithium is now in period 2. So we need to add a second electron shell. And I'm not sure I'm going to, I'll do one more, I'll do lithium. So the third, or the second shell has an S going one way, which holds 2 electrons. Then it also has a P suborbital that holds 6 electrons. And you would have been examined on this last year, but it's always good to have a quick rehash because it helps other things make sense. So lithium has 3 valence electrons because it's 3 electrons, sorry. It's in group 1, so it has 1 electron in its outer shell. So we know the s orbital is full. We then do 1s2, 2p1. Then we create another box for the p orbital, and we fill it like this. So there's a quick rehash on your Lewis structures. I'm not going to go over that anymore because you've already got assessed it. But it's good to get a overall look back at it. So now let's get to the actual interesting thing. And this is where most people get tripped up. They try and take on organic chemistry without really understanding the bonding behind, the science behind the bonding that happens in organic chemistry. So when we have a metal and a non-metal, we know it's an ionic bond. We then have the covalent bond. So this can be broken up into 3. We have non-polar, polar, non-polar. We can also add in hydrogen, which is just a special form of polar bonding. And this is all determined by that electronegativity. So when we have an ionic bond, it's all determined by the electron configuration of the atom. The reason that we don't so much look at the transition metals is because they can transition between multiple oxidation states. When we're looking at ionic bonds, metal and non-metal. So this is a purely electrostatic attraction. You have a positively charged metal and a negatively charged non-metal. So if we have a covalent bond and it's non-polar, so electronegativity difference of less than 0.5. What that means is if we have hydrogen and carbon and they're sharing that outer shell, the electrons are spread evenly between hydrogen and carbon. No one is hogging. Non-polar is the opposite. Well, not quite the opposite, but just there. So we have carbon and oxygen. Carbon is less electronegative than oxygen. So what happens is oxygen already has 2 unbound electrons on it when it's bound to carbon. I don't know if you can see that on the whiteboard actually. That's small. So you've got 2 unbound electrons, and because of its extra electronegativity, let's say it's hogging 6 electrons. Carbon only has 2. So what we end up with is a negatively charged end at oxygen and a positively charged end at carbon. The carbon end is positively charged, the oxygen end is negatively charged. This might be ringing some bells for organic chem, because on your esters, aldehydes, and ketones, you have a carbon to oxygen double bond, and they're all polar. So this is important, again, for your organic chemistry, because another carbon to oxygen molecule can line up next to it. With all its extra electrons here and only 2. So this end is effectively positively charged. This end is negatively charged. And you get an attraction between the 2 atoms. There's a big distinction here between these. Okay, I should get rid of that from under there for now. These are intramolecular, as in they hold the molecule together. Then we have what's called intermolecular, which is this. So they're holding carbon to oxygen together. So now let's look at intermolecular forces. So these are intramolecular, ionic and covalent bonds. We have non-polar bonds where the electrons are shared evenly. Then we have polar bonds where they are not shared evenly. So they are the intramolecular, We have the ionic and the covalent. Now let's look at the intermolecular. As in they hold two different molecules together. So we have dispersion forces or London forces or van der Waals. Again, this is part of unit 2. We have dispersion forces. We then have dipole forces. We then have hydrogen bonds. Dispersion forces occur in non-polar substances. Anyone that's had organic chem tutoring? That's hell. Anyone that's had tutoring with me will know that I harp on about these, but they do form the basis of a good chunk of units 3 and 4. Non-polar bonds, non-polar molecules have dispersion forces holding them together. Polar molecules have dipole forces holding them together. When we have hydrogen bonds, they're still polar, but they're a special kind of polar. Special kind of polar. Now, let's remember these are intermolecular forces. They are not holding the molecule itself together. They are just holding two molecules, an attractive force between two or more molecules. So let's start with dispersion forces. Dispersion forces, the weakest kind. They are weak, they are fleeting, they occur because if we have a hydrogen molecule, at some point we can assume the electron is over this side. Hydrogen only has one electron. So we have this side is very, very weakly negatively charged. This side is very, very weak positive charge. We have another hydrogen come over this side. Its electron is over here. And you get a very slight attraction between the two. So that's dispersion force. They are weak only between non-polar molecules. So we've got after that. Now, I'm probably just going to jump straight into the hydrocarbons after this. So remember this, when it's hydrogen down to carbon. We have dipole forces, meaning that, like a magnet, it has a negatively charged and a positively charged one. So we have on this side, we might have carbon, and it's double bound to oxygen. Now, the oxygen and the carbon are supposed to be friends. They're supposed to be sharing the electrons evenly. They don't, because we know that oxygen has a higher electronegativity. So we have a negative charge on the oxygen side. We get another one of these molecules, come over here. Same thing, the oxygen is hogging the electrons, the shared electrons, and we get some interaction. This is about 1/10 the strength of a covalent bond. So they're not super strong, but they're not weak. They're about in the middle. They are not as fleeting or short-lived as the London forces or Van der Waals forces. And the next step up we have, if you're trying to recognize what has dipole forces or what is a polar molecule, look at the question, find where you have which of the elements you have, go to the periodic table, go to the information at the back, compare the electronegativity values, and it will tell you. If it's greater than 0.5, we have dipole forces present. Then we have hydrogen bond. Hydrogen bond. So we have in here, we have oxygen, so nice cheap for everybody, oxygen, nitrogen, or fluorine bound to hydrogen. Now, why is this special? Hydrogen has an electronegativity of 2.2. So oxygen or nitrogen is 3.0. So the difference is 0.8. Oxygen is 3.5. So I have a difference of 1.3. Fluorine is 4.0, so we have a difference of 1.8. But the other interesting thing is nitrogen and oxygen both have an unbound pair of electrons, which contributes to the negative pole. So if we have the classic example I'll draw on the board is water. So we have oxygen bound to hydrogen. Now the oxygen already has 2 unbound electrons, so it's already negatively charged. The hydrogen both share 2 more electrons. Oh, sorry, each share 1 more electron. So the oxygen effectively is now super duper negative charge. So you have a plus on each of the H's because oxygen has stolen its electron. In dipole forces, it's hogging them. So eventually it will come back to the carbon from the oxygen. But for this, they are effectively stolen by the oxygen. So it's got 4 times the negative charge that it should have. So we have another oxygen molecule over here. And this attraction between the super negatively charged oxygen and the positively charged hydrogen is the reason why. Draw another one over here. Creates this web shape. So you end up with, and we can put another oxygen down here for good measure. So these oxygen can create new bonds with the hydrogen to create this diamond structure. And this is what gives water its unique properties. When water freezes, these bonds flex outwards. Everything else in nature that we know of, the volume decreases when you freeze it. With water, it increases. The crystals of ice actually push the bonds further out. Go and test it, put a plastic water bottle in the fridge and freeze it and see what happens. And we can bring this back to boiling point. Melting point, how brittle something is, how strong something is, conductivity. And this is really, really important to understand for the quite hardcore organic chemistry that we'll get to in units 3 and 4. So let's look at basic hydrocarbons. And this will finish Unit 2. So we have the hydrocarbons. As the name suggests, made of hydrogen and carbon. These are all of our fuels. So methane, ethane, propane, butane, pentane, hexane, all what we burn in our barbecue. Octane is what makes our fuel burn hot. So the higher the octane value rating, the hotter the fuel burns. And this makes up the backbone of everything you're going to do in organic chemistry. So if we were to look at what organic chemistry was, it's all based around carbon. Carbon is in group 4. It can form up to 4 bonds. So the very, very first, most simple organic compound is methane. And absolutely every other organic compound builds off this backbone. We can make it longer. But it's still just carbon and hydrogen. And these are what we call saturated hydrocarbons, because they are completely saturated with hydrogen. So if we look at, we can name these basic, we call them alkanes. They are the most basic. of. So when we're looking at organic chemistry, everything has this carbon backbone. Alkanes are the backbone of everything. So when we're naming them, we're not worried about the hydrogens. We're worried about the number of carbons. So 1 carbon is with 4 but 5 is hex. Sorry. Yeah. So we'll go to 4, we'll keep it simple. So the first thing we do, how many carbons? 1, 2, 3, 4. So the first part of the name, but but. So then we would look at, we need to look at what kind of bonds are here. So 1, 2, 3, 4, they're all single bonds. They're all single bonds. So we call this an alkane. Or in this case, we would call it butane. So this basic naming convention rings true all the way through organic chemistry. 2, 3, how many carbons in the backbone? What's the longest carbon chain that is present? What kind of bonds does it have? And we're going to skip straight into unit 3, and we'll just keep going along with this tag, and then we'll switch out from organic. So if we have, let's keep that there. I will send out loads of resources and lecture slides and stuff so that you can put this into context. So if we have, what about if we had a double bond? Yeah. So we get one of these hydrogens, and instead we have a double bond. The number of carbons doesn't change. But instead of calling it butane, we call it butene. So this is now an alkene. So alkanes is single bonds. An alkene, double bonds. Alkyne, triple. So if I was to get rid of this hydrogen, give it a triple bond, it would be called, we call it butane. Now there's 10 other organic compounds you need to know. And the way that we identify what kind of organic compound it is we can look at the functional group that is attached. So if we were to have an alkane with only single bonds, its functional group is the fact that it doesn't have a functional group. So the lack of a functional group is its functional group. The functional group gives the organic compound its chemical properties. Gives it the chemical properties. If it was an alkene, this double bond here is what gives the organic compound, or that alkene, its chemical properties. If it was an alkyne, that triple bond is what gives it, again, its chemical properties. Right, I'm just going to pause the recording for 5 minutes and we'll come back and jump straight into Unit 3 and 4. Hi everyone, welcome back to the first hour. We're going to jump straight onto Unit 4 because we've finished on the organic chemistry, and then we'll go back to Unit 3 for the redox reactions. I expect organic chemistry Unit 4 to take probably an hour to an hour and a half. And then Unit 3 with the redox reactions, electrochemical cells and stuff to take up the rest of the time. And a bit of acid base as well. I think maybe it was slightly, what's the word? Adventurous to try and get through all this in 4 hours, but we'll do our best. If I have to do another recording with a bit more, I will, that's fine. So we know that the functional group determines the chemical properties of the element. So we have our hydrocarbon backbone. So alkane is, well, the functional group for an alkane is actually the lack of a functional group. It just has single bonds between carbon and hydrogen. Alkene has a double bond between two of the carbon atoms in the backbone. That's its functional group. An alkyne has a triple bond. So there are basic hydrocarbons. It does get a bit more exciting than that, because we can add the other functional groups on. So we have an alcohol, which has a hydroxyl functional group. Has OH on the end. It has a substantial impact on the physical properties of ethane, which is a gas that we burn for heat and to cook with, and we turn it into ethanol, which is the active ingredient in liquor, in alcohol. This is what makes people feel at ease, anti-anxiety. Whereas if we just had the H on there as an alkane, it is a flammable gas. So changing the functional group has a massive impact. So if we had an amine group, we would have three hydrogen attached. So this is an amine. So your amines are all of your biologically active molecules. Codeine, morphine, benzodiazepine, all of your nucleic acid stuff is based around the enes. We also have the aldehydes, which you'll see carbon to oxygen double bond and a H. So these are the aldehydes. So now we're looking at polar bonds. So the big aldehydes and ketones both have this functional group, the carbon to oxygen double bond. Aldehydes, you can recognize them because they're always on the end. So they'll always be attached to a hydrogen. Whereas with our ketones, they still have this same group here, but instead it is on the middle carbon. So that's a ketone. It's attached to two carbons. The aldehyde will be on the end because it's attached to a hydrogen and a carbon. So the other common one is carboxylic acid. So if I was to then add QCAA is the carboxylic acid functional group. We then have an amide group. So we had the amine group, which was NH3. Then we have the amide functional group, which is NH2. So they're your main ones. There are a couple others that I'll introduce, but they are the main functional groups. And they drastically alter the original carbon backbone, which is just the alkane. So let's head back to the alkane. So now we know the functional groups. We know what they look like. Let's go back to a little bit back to the alkanes. And when we're looking at isomers, so isomers are mirror images of each other. Or another way to put it, a lot of the time, they have but they differ in their structure. Same chemical formula, different structure. In 3D space and in a straight line. Sorry, it's an invasion by a toddler. Just bring up some notes that I'll send to you guys. So we have structural and stereo. Structural isomers. And then we have stereo isomers. So again, same chemical formula. Different 3D shape. Same chemical formula, different 3D shape. So an example of this, I'm going to move fairly quickly. I think I underestimated how much we need to get through. I might do this session and then another maybe hour or two as well. It's organic chemistry is probably going to take most of this session. So let's look at the structural formula of C4H10. So this would be butane, so depending on your teacher and how they're teaching, they may do these line this way, or they may do it with the lines, with the points. And each point, if we were to draw it like this, represents one carbon. So 1, 2, 3, 4. It's just a different way of representing. This way is easier to understand. So this is butane. But we can also draw C4H10. It's 2-methyl propane. So it would look like something like this. So you can see they both have 4 carbon atoms, still both longest chain so we have 4 carbon atoms still H10. There's 2 things to remember here. We name the backbone based on the longest continuous carbon chain. So this is 4, so it's butane. Over here, the longest continuous chain is that way is 3. That way is 3 as well. So this is an isomer of each other. And it's what's called a chain isomer. So the changes in the structure of how these chains are. So let's stick with looking at naming this molecule here. So this is, we have carbon here. This is what we call an alkyl sidechain. This is the backbone, or this is the backbone or the longest continuing chain. Which is 3. So in order to name this, we can't just use the same old way we did with the alkane and alkyne. It's a little bit different. So we number the carbons so that the carbon that has the side chain coming off it is the lowest number possible. This makes it nice and easy. 1, 2. It doesn't really matter which way you name it from. Not a big deal. Which way you number it from. So what we do is the name starts with the position of the carbon that this alkyl side chain comes off. So we call it 2. Okay, so remember back to our naming convention. And back to our naming convention. 1 carbon is meth. So we call it 2 meth. And we just take the YL of the side chain. So 2 methyl. And then we find the longest continuous chain. Not how many carbons there are. The longest continuous chain. Which will be 3. We remember what 3 is. 2-methyl propane. We name using the second carbon because that's where the alkyl side chain is coming off. We look at the carbon here, it's only 1 of them. So it's meth, 2-methyl prop because there's only 3 carbon atoms. So that is how you name the chain isomers. It gets a bit more complicated when we're looking at multiple chains. So we're looking at example, if we were to have, just for sake of speed, I'm going to draw it like this. So if we have, this is what we call a chain isomer. So the first thing we do is we find the longest continuous carbon chain. We know that it's 5 carbons, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. So it's going to be pent. We know that there's only single bonds present. So the parent or the backbone is going to be called pentane. Now, which way do we label? We want both of these to have the lowest number possible. And this carries through no matter you're into 3rd and 4th year organic chemistry. It doesn't matter. This rule still applies. So we count from this side because that gives us, use a red pen, 1, if we were to count from this side, we would have 1, 2, 3, 4. So we count from the left. Now, this is, and when you're answering these questions, it's good to just write down, okay, so we have pentane. We then have a methyl group coming off the 2nd carbon. So it will be a 2-methyl. Instead of trying to write the answer in one go, just write some notes on the side for yourself. Now, this has still an alkyl sidechain, but it has 2 carbons. So it's coming off the 3rd carbon, and we know that if it has 2 carbons, it's pronounced F or eth. So now we just have to put it together, combining the name. We just list them in alphabetical order. So pentane will always go on the end. The functional group, ane, ol, al, il, always goes on the end. So E comes before M, so it would be 3-ethyl, 2, oh no, it would be a dash, 2-ethyl pentane. So 2-methyl pentane. Because we have the longest continuous carbon chain is 5 carbons. Either way, doesn't matter. It's coming, a methyl group coming off the 2nd carbon and an ethyl group coming off the 3rd. So that's how we name with 2 different side chains. The other one is called a positional isomer. And this is when only the position of the functional group varies. So we have let's keep it simple. Actually, no, we can't do that because it's going to be a so what this would be, so we count 1, 2, 3, 4. So it would be bute. Again, we number the carbons based on giving the functional group the lowest number possible. So 1, 2, 3, 4. Bute 1, and we name it based on the functional group. So it will be bute 1. So, if I were to change the position of this functional group, put it here. It's exactly the same. The functional group is coming off the second up. So it would just become Bu2. But the thing to remember is they are isomers of each other. That's how we name positional isomers. We also have these, what we call stereo isomers. They're what we call geometric isomers. And that's when they're connected in the same order, but they have a different arrangement in space. Looks something like that. So they're attached in the same order, but they've just rotated around the single bond. We have a cis isomer, or this is called a trans isomer, because these hydrogens here are on different sides. They've gone to the other side. If we had a cis isomer, it would be both of the hydrogens, in this case, are on the same side. So they would have the same formula, but very different arrangements in space. And this is really important when you look at biochemistry later on at uni, if you're planning on taking that path. Okay. So I'm going to move through organic chemistry probably over the next hour or so, and then see where we land. Scrub some new notes. Okay, I'm going to touch back on intermolecular forces, because they are by far the most important thing to understand. And let's put it in the context of the hydrocarbons first. So we know hydrocarbons are made up of carbon bound to hydrogen. We should know by now that the hydrocarbons are non-polar molecules. There's no polarity in their bond. So they have low, I'm just going to shorten it to IMF, or intermolecular forces. So we should know that low intermolecular forces will give us a low boiling point. So non-polar molecules, if we look at the hydrocarbons, we can see that methane, the most simple organic compound, has a boiling point of minus 189 degrees. So that's right, methane. One carbon, 4H. So its boiling point minus 189 degrees Celsius. If we take a look at, actually let's look at ethane, probably a better example, is minus 89 degrees Celsius. If we were to have an alcohol group attached, still only has one carbon, but it has hydrogen bonding. So it has a boiling point of 78 degrees Celsius. Because it has higher intermolecular force. Now we can take this even further to ethanoic acid. Has a boiling point of 118 degrees Celsius. Now, they still only has, well, 2 carbons, sorry. Change it from methanol. 2 carbon, 8 hydrogen. Still only has 2 carbons in the backbone. So, this is the impact the intermolecular forces have on the boiling point. Now, I'll go back to that point of these are intermolecular forces. They're holding 2 molecules together. When you add enough heat to overcome the intermolecular forces, liquids become gas. So we're going to concentrate on the hydrocarbons first. So they have nonpolar forces, or nonpolar bonding. So they have a very low boiling point. Now, something to consider that the more carbons in the backbone, the higher the boiling point. So more carbons, higher boiling point. So methane has a boiling point minus 162. Ethane is minus 89. Propane minus 45. All the way up to decane, which has 10 carbons. And all we've done is add more carbon. It has a boiling point of 174 degrees. We then have, and this is because if we consider methane, we know that the interaction is between the hydrogens. So in methane, there's only 2 spaces for this bonding to occur. If we have, so this is ethane, if we have methane, sorry, not methane. We have, let's go with butane. We have 4 carbons, which means there's twice as many spaces for this bonding to occur. So the longer the chain, the higher the boiling point. The longer that backbone, the higher the boiling point. Now this gets kind of thrown to the wind a little bit if we have molecules with a chain. So if we had, 4 carbons, and they're arranged like this, there's effectively 10 spaces for hydrogens to bond to other hydrogens. Whereas if we have, say, a chain or a not straight chain molecule. When another, so we have hydrogen, the shape just doesn't allow it. Another carbon atom, it just doesn't fit together as nicely. So when you have a chain on the molecule in a hydrocarbon, the boiling point will be lower. If we go up to the aldehydes, ketones, and esters, so aldehydes, ketones, and esters all have this carbonyl group, which is carbon double bound to oxygen. So carbon is significantly more electronegative than, sorry, oxygen is more electronegative than carbon. So we have a negative pole here and a positive pole here. So these will have both these polar or dipole forces as well as the aforementioned dispersion forces. So if we have a hydrocarbon and an aldehyde, ester, or ketone that have the same number of carbons, the aldehyde, ester, or ketone will have a higher boiling point of something with a very similar mass. What happens is we have negative, positive. Another molecule comes along. And you get this intermolecular forces between the molecule. That's with a ketone, aldehyde, and an ester. So they will have a higher boiling point than your hydrocarbons. So next we have the alcohols, carboxylic acids, amines, and amides. So these all have oxygen bound to, hydrogen bound to oxygen, nitrogen, or fluorine. So they have a hydrogen bond. So these will have significantly higher boiling points. So they have hydrogen bonds, polar bonds, or dipole forces, I should call them, as well as the dispersion forces. So they will have significantly higher boiling points than the esters, aldehydes, and ketones, as well as the hydrocarbons. So if we look at, let's draw a nice pretty picture. We have ethanol, so hydrogen is positively charged, oxygen is negatively charged. Along comes another ethanol. So this is negatively charged, and you get interactions between the negatively charged oxygen and the positively charged hydrogen on the other side. So ethane, which is our hydrocarbon, which is just minus 89 degrees. We add OH, or a hydroxyl group, it becomes ethanol, and the boiling point is 78 degrees. The only difference being in the level of, or the level of intermolecular forces between the two. So, amides and amides also have hydrogen bonding, but it's due to the nitrogen, which is, it's exactly the same idea, is that they have higher intermolecular forces than the hydrocarbons. So there's one exception to this rule, and it's the carboxylic acids. So if we look at the way the other functional groups create bonds, it's just straight between H and O of this molecule here and this molecule here. It's only a single hydrogen bond between two alcohol molecules. If we draw a carboxylic acid, it produces dimers. So the classic exam question is, which of these organic compounds will have the highest boiling point? If you see these carboxylic acids, even though it's still hydrogen bonding, it will have a higher boiling point because it has the ability to form dimers. It actually creates two links between the carboxylic acid molecules, which gives it a significant advantage. So ethanoic acid has a boiling point of 118 degrees. Ethanol is 78 degrees. Both of them have hydrogen bonding, it's just that carboxylic acids have two sides. So if we were to draw it like this, carboxylic acid's a COOH. So over this side we have a negatively charged oxygen, over here we have positively charged hydrogen. So we now have two separate sites for hydrogen bonding. So what happens is we get another carboxylic acid comes over here. So we have two sites for hydrogen bonding. So the classic exam question will ask you which of these compounds has the highest boiling point. They'll likely give you a hydrocarbon, an aldehyde, ketone, or ester, and then ask you, as well as a carboxylic acid, and maybe an alcohol. So you can immediately get rid of the other two, then you have to look at the two hydrogen bonds. So if there's a carboxylic acid or COOH on the end of a molecule, it will have the highest boiling point. This other is volatility. is another part of organic chemistry. So it's the opposite of boiling point. The intermolecular forces are so weak that they will just fly off into the air. We also have melting point. So the longer the carbon chain in the organic molecule, the higher the melting point. So this is because of those increased intermolecular forces. So they follow the same rules as the boiling point. So they're asking you about melting point. Just think what would have the highest boiling point and you get the same answer. All right, what's the time? All right, let's get through solubility in 13 minutes. So the biggest rule in solubility is like dissolves. And again, I will keep drilling the intermolecular forces into you. This means they have the same intermolecular forces. So, water doesn't dissolve oil. If two things have same intermolecular forces, like dissolves like, they can dissolve into each other. So hydrocarbons can dissolve other hydrocarbons. They talk about water as the universal solvent because it can dissolve everything except the hydrocarbons. So all the other organic compounds, it can dissolve. If we try to mix alcohol, it won't work. Have to have the same intermolecular forces. And I'm just going to try to demonstrate what actually happens when two things dissolve into each other. So we have, let's have pentane on this side and octane on this side. They're both hydrocarbons, they just have different backbone lengths. So we have our pentane molecules over here. They're being held together by dispersion forces. Very weak. And then we have octane over here, which is also held together with dispersion forces. When we mix these together, what actually happens is that these bonds are dissolved, they break. So we mix these two together, all these bonds disappear. Now, if they're both dispersion forces, they will reform new bonds with each other. So they will become effectively the same substance. So they will become dissolved within each other. But if I was to put, say, water or an alcohol in there, it wouldn't do the same thing. Those bonds would break, but they wouldn't reform. There's one group I haven't mentioned yet, but I will because it will come up in a second. The halo alkanes. So this is just an alkane. Instead of a hydrogen, we have bromine or iodine or chlorine or fluorine attached instead of the hydrogen. They are slightly polar, so they will dissolve. The smaller haloalkanes will dissolve in water. So same thing with, we look at, let's just look at solubility in water, which is has hydrogen bond, it's a polar molecule. The aldehydes and ketones, they have a carbon, oxygen double bond, so they are polar, they have a negative and a positive. But they only have this one site. So in water, they are slightly soluble. So if we look at alcohols, we know that alcohol is very soluble in water because, well, there's alcoholic drinks. So the alcohols in the carboxylic acids, the alcohols in the carboxylic acids will dissolve into water very readily. We know that the carboxylic acids have that, just like with the boiling point, they have two sites for hydrogen bonding, whereas the alcohol only has one. So if we look at our carboxylic acid, something like this, so we then put two water molecules, the oxygen will bind with the water, with the hydrogen, and the hydrogen will bond with the oxygen. So they say that ethanoic acid has unlimited solubility in water, whereas alcohol is just very soluble. It's a really weird, vague terms they use in organic chemistry. We know that the intermolecular forces present affect the solubility. But also, remember back to that molecular shape, if it has any chains on it, then we need to be wary of that. Straight molecules that have are in a straight line have higher solubility than those that are chained. So again, it's because these molecules, you can pack them closer together, whereas the branched compounds, there's less interaction between the solute and the solvent, so the solubility is lower. All right, I'm going to take 3 or 4 minutes again and get stuck into the end of the organic chemistry module. So now we are into the nitty-gritty of the organic chemistry, which is the reaction pathways. So this is where you say, what, under conditions of UV light and heat, what would I get if I mixed an alkane and a halogen? This is probably the biggest part of your organic chemistry, how you actually apply all of the knowledge you have to how you can shift around. So if we have say we have a Let's go with something simple. And we'll stick with the alkanes. Well, this is what's in the syllabus. So the alkanes, haloalkanes, and the alkyl. How can we turn them into all of the other organic compounds? Well. We have a substitution reaction. We have addition reaction. Then we have an elimination reaction. So substitution, we swap one molecule out for another. Addition reaction is where we add molecules. Elimination is where we remove molecules and we put in a double bond. Fairly self-explanatory. One thing I do want to go over is combustion reaction. In a combustion reaction of, say, hydrocarbon, you have the hydrocarbon, so let's say methane, CH4, with 2 oxygen creates CO2, H2O, and energy. Thing to remember with a combustion reaction is there is nothing left of what was originally there. The methane and oxygen is turned into CO2, water, and energy. I'm not going to go too much into that. We have a substitution reaction. So let's try and get through this in 30 minutes so that we can move on to some of the other parts of Unit 4 and Unit 3. So we have alkanes. So the thing to remember with this is that the reactions with more than one step is outside the scope of Year 12. It will not be assessed on it. It's only these single step reactions. Lucky for you guys. So if I react an alkane with bromine, which is a halogen, the more reactive halogen replaces the hydrogen. We end up with bromine on the end instead of hydrogen. So this produces a haloalkane from an alkane. So we've substituted bromine for the hydrogen. That's the simplest form, and it always happens in the presence of UV light. UV light weakens these bonds with hydrogen. Bromine, which is more reactive, comes in, goes, whee, I'm going to steal that, and attaches itself to the bromine, to the carbon. So alkane, presence of UV light plus a halogen creates a haloalkane. That's the first one. We then take our haloalkane and we react it with bromine again. Same thing happens on a different hydrogen. We end up with a dihaloalkane. So same thing, substitution. We just now have 2 bromine or 2 alkanes, so we call it a dihaloalkane. So the next set of reactions is we go from a haloalkane, so alkane with a halogen group, to nitrile amine or an alcohol. So 3 possible pathways, 3 possible reactions. If we take our haloalkane, so in this case, we have iodine as our halogen. We react it with cyanide, because why not? And in the presence of heat, it will take away the iodine and substitute it for instead of having a haloalkane now, we've substituted the functional group for a nitrile functional group. This is what all of your nitrile gloves are made out of. So presence of heat and cyanide, we swap out our haloalkane and we produce our nitrile. So again, I'm going to work through this pretty quickly. If we add, so we know our amine group is NH2 or NH3. In this case, it would be NH2, but we add NH3. This produces our amine. So instead of the iodine being there, the NH3 reacts with it, kicks the iodine off, so then we end up with a nitrile. So we've kicked off our iodine. Now we have NH2. So that's how we go from haloalkane to an amine. Haloalkane to an amine. And in order to add to this, you just have to remember the functional group. So the exam question asks you, how do I go from a haloalkane to an amine? Well, if you don't know what the amine functional group is, which is NH2, then how are you going to know what to add to it? So we can also create, and if it asks, the exam question will ask, we take a haloalkane and we react it with OH minus or a hydroxide ion. What are we going to get? Well, OH minus is more reactive than the iodine, so we'll end up with same molecule, but with oxygen and hydrogen on the end, instead of iodine. So we go from an haloalkane to an alcohol. So if you understand what the functional groups are, when we're swapping them around, we take our haloalkane, we add cyanide or Cn minus. It's more reactive than iodine. So it will kick iodine off and it will substitute itself in there. Alcohol, OH minus, is more reactive than iodine. It kicks iodine off. The difference being with the hydroxyl group, it doesn't require any heat. So it's what we call the nuclear fire. Again, that's probably a bit above where you need to be. Okay, that's the 5 different substitution reactions. So now we're looking at the addition reactions. As the name might suggest, we're adding molecules. So we go from an alkene to an alkane. So we're breaking the double bond by adding molecules to the alkene. So if we take our alkene and we add 2 halogens, Br2, what that does is it actually gets rid of this double bond. It's not an alkene anymore. It becomes a dihalo alkane. So 2 halogens, so dihalo halogens, and alkane because it's all single bonds. So we've gone from our alkene to a dihalo alkane. So what we've done is we've added, so here's the trick. If you're adding something to an alkene, it's going to become an alkane. So if you're adding 2 halogens to your alkene, it's going to become an alkane. We can also do this if we add water, and here's where it gets a bit weird. A lot of these reactions previously happened relatively spontaneously in either the presence of UV light or the presence of heat. If we add water to our alkane, in the presence of and around 300 degrees Celsius of heat, then we will end up with ethanol. It's not exactly spontaneous. So we can take ethene or ethylene, react to the presence of water, hydrogen phosphate, 300 degrees Celsius, and produce an alcohol. But again, just remember, okay, we're adding water to an alkene. That means the alkene is going to become an alkane again. Doesn't exactly happen spontaneously. So we have one more addition reaction. So if we remember the addition reactions are adding molecules to the double bond to break it. So we can add HCl or hydrochloric acid. We will end up with it becomes halo alkane again. So we react the alkene, the hydrochloric acid attacks the double bond, breaks it, and attaches hydrogen and chlorine to make a halo alkane. So I'm moving through these pretty quickly. So we have the 2 final reduction reactions. So the 2 final reaction types. We have a reduction reaction. which is the opposite so we have a reduction reaction where we are going from alkene to alkane. Then we have our elimination reaction. So we're going from a halo alkane so again, another one that occurs in the presence of NaOH or a strong base or reducing agent, as well as heat. We actually create the double carbon to carbon double bond again. So we go back to, so we go from a halo alkane back to just a straight alkene. There's a couple of side effects of this reaction. We produce water. So the OH reacts with this hydrogen. So the OH binds with this H to produce H2O. And the sodium binds to the chlorine. So we end up with H2O and NaCl. So now we've used our strong base, which reacts with H to produce water. So what we've done is we've mixed an acid, which is the halo alkane, with the base, sodium hydroxide. We get rid of the H, we get rid of the Cl, and we end up back at an alkene. Now the final reaction is the addition reaction. So if we take ethylene, take ethylene, we add hydrogen, and lo and behold, we create back to our alkane. Another process that doesn't just happen spontaneously. Requires a catalyst. Again, I'll send you the all of these materials and resources once I've sorted them out after this. And that is the end of organic chemistry. So we've just done about 18 hours worth of organic chemistry in an hour and a half. So well done. This is not something to base all of your exam revision on, but it's a glossing over the topics you need to work on. Now, I'm probably not going to get through them all, so I will run another session after this. But took about as long as I thought, so I'll just pause for a minute. Okay, so we've finished organic chem, jump into the industrial chemistry stuff, and we'll just look at the Haber process. So this is all your equilibrium stuff. I'd be very surprised if there wasn't a question about the Haber process, Haber process, whatever you want to call it, in your final exam. So I'm not going to go through all the boring stuff. So ammonia is NH3. The Haber process, Haber process, whatever, is as a gas plus 3H2. And you have this funny looking symbol. So that symbol is for chemical equilibrium. I don't want to think how long this is going to take to upload. It's going to be quite a long process. So the Haber process, now we're looking, think back to Unit 1, a glorious unit when you did Hess's law. Everybody loves, including me. So the change in heat is minus 92 kilojoules per mole, which means that each time this reaction progresses, 92 kilojoules is released per mole of NH3 that is produced. So it is exothermic. Now we produce ammonia. Actually, I know there's a practice question in one of the practice questions on the Haber process, so it will definitely be in there. So when we're looking at this dynamic equilibrium, we can talk about three things. Pressure, or two things. Pressure, temperature. So if we remember back to Le Chatelier's principle, which is in Unit 3, if we change, but I'm not going to go back and go through it all, I'll just speak about it in the context of here, but if you're struggling to understand this, go back to the Le Chatelier's principle, definitely don't care. So if we change the condition in our, let's say this is our reaction vessel, the equilibrium will change to either favor the right-hand side, which is the product, or it will break down the product to favor the reactant side, which will re-establish the equilibrium point. Now we can use this to our advantage. So if we increase the pressure, so the pressure is caused by gas molecules bouncing off the sides of the container. So if I increase the pressure, I can safely assume this is also a gas, my bad. I increase the pressure inside this where this reaction is happening. The system will push the equilibrium to producing the product. Why? Because over here we have 4 moles of gas. So there's less gas particles. Over here we have 2. So in order to bring that pressure back down, the system will favor the product. So we up the pressure here, we increase the yield. We take the temperature, We know it's an exothermic reaction. If I drop the temperature, the equilibrium will shift again to produce the product, because producing ammonia releases heat, which will bring the temperature back up to normal, which will increase the yield. So I'm not going to go through everything with this, but let's look at it if I drop the pressure, there's 4 moles of gas over this side, so the equilibrium will shift to break up ammonia. It will shift back this way, so the yield will go down. If I increase the temperature, then the system will seek again to go back this way, because going back this way absorbs the extra heat and brings the equilibrium back to normal. So if we have an exothermic reaction and we want to increase the yield, we drop the temperature as far as we can. Now we can't just keep dropping the temperature, because we know that the rate of reaction is based somewhat on the temperature of the reaction vessel. So we can use what are called catalysts, because there's a limit to how much pressure we can use, and there's a limit to how low we can drop the temperature. If we drop the temperature too low, it will take so long to get to that extra yield that it's not worth it. So we use a catalyst. The catalyst for this is magnetite, which is Fe3O4. So it's finely ground and increases the surface area. And what it does is it lowers the activation energy required for the reaction. So the idea is that we have to balance the conditions. You can't just jack the temperature up or the pressure up, because it will blow up half a city. So that's all I'm going to do on industrial chem. I could talk for hours, but when you're looking at this in chemical equilibrium, you need to understand what can change the conditions, what will happen to the equilibrium, which side will it favor. You can do that by knowing, is it exothermic, is it endothermic, and which side has the most gas molecules. Bring the next set of, so I'm trying to pick. Okay, so let's think back to the biggest changes that move stoichiometry into grade 12, which I think is crazy, but we have to do it. So we have this called a theoretical yield. So if I mix 1 plus 1, I should get 2. Theoretically speaking, of course. Sometimes it's not possible to get to the conditions for 1 plus 1 to equal 2. So if I mix X amount of 1, X amount of 2, theoretically I should be able to produce this much. And I'm going to actually use a different example. So bear with me. Calculate all of this. And this is called stoichiometry. And it is the bane of my existence. And soon will become the bane of every chemistry students. So I've got the example here, and we're using the Haber process again. My guess is there's going to be questions with the Haber process. It's going to have that chemical equilibrium, and then they're going to start talking about theoretical yield. It makes sense in the way they presented the materials. It would be a bit silly not to be perfectly honest. So, my question that I'm going to use. So, this is a worded question that we need to put into chemical terms. So, this is a big part of exam prep. It's actually learning what do they want to see, how do they want to see this answer. So, the question goes, in the industrial synthesis of ammonia. Okay. Synthesis is 1 + 1, or A plus B equals AB. So, in the industrial synthesis of ammonia, bracket NH3, close bracket, N2 and H2, right. First thing I do is I write down the reaction. So, N2 is going to produce NH3. Brilliant. We've got our unbalanced equation. Many students get to your final exams in year 12 and they've forgotten how to balance an equation. It happens far too often. So, first thing we need to do is balance this equation. This is unbalanced. We count the amount of molecules on both sides. So we've got 2 nitrogen, 2 hydrogen, this side, we have 1 nitrogen and 3 hydrogen. So, it's common denominator between 3 and 2 would be 6. So we would balance nitrogen first, so 2 NH3 with 3 H2. We check out working. Okay. Yeah. 2 nitrogen, 6 hydrogen. It's balanced. If you don't balance the equation correctly, you might as well not continue with the question because it's going to be wrong. This is the basic stuff that you need to get right. So then the rest of the question goes, N2 and H2 react at high temperature, but they never react completely. This means that either nitrogen or hydrogen is going to be the limiting reagent. Now, the rest of the question reads, in a typical reaction, 24 kilograms of H2 reacts with 84 kilograms of N2. This produces 68 kilos of ammonia. These are the kinds of questions that they're going to ask you because it puts everything that you've done in chemistry so far together. So, we know, well, we should know, that when we're talking about chemical reactions, we don't use grams. We need to know how many moles of something there are. In order to correctly determine which of these will run out, I use this question as an example all the time. But everybody says hydrogen. It will be the limiting reagent. So in reacting these two, one of them runs out first, and we're stuck at a maximum of 68 kilos of ammonia for this reaction. What we need to do is convert it into moles. So some terminology. This is the actual yield. the rest of the question will ask you to find the theoretical mass of ammonia. So we need to find out, if I mix these two together, in a perfect world based on this equation, how much ammonia would be produced? The answer is it'll never be 100%. Once we've found the theoretical yield, we divide it by the actual yield, and that gives us a percentage number. And that's what we're after. So now we need to determine which one of those two is going to be the limiting reagent. So we do that, we need to convert from grams into moles. So let's do nitrogen first. And this is my frustrations at the moment, is that these are the very basics of what you did in grade 11 and 12, and a bit in unit 3 is the mole, concept of the mole. So we know the molar mass of hydrogen is 14.01 grams per mole. Every 14.01 grams of nitrogen, there are 6.022 times 10 to the power of 23 moles. So the way we convert is we take 84,000 grams, we divide it by molar mass of nitrogen, grams per mole, times 2 because it's N2. So what this does is it cancels out, dividing both sides by grams. So that should give us 3,000 moles of nitrogen. So now we know how many moles of nitrogen we have, as opposed to how many grams, because grams doesn't tell us how much, or how many, sorry, just tells us the total weight of what's there. So if we are looking at which of these are going to run out first, we need to know how many there are. So if we were to do hydrogen, so hydrogen is 1.008. And the big difference between a really, really good score and a pretty good score is these units. Use the units correctly, round up and down, use the correct number of significant figures. And even if you get the answer wrong, you'll still get marks for it. So 24,000 grams of hydrogen divided by the molar mass of hydrogen times 2. And that will give us 11,900 moles. But this isn't the end of the story for this. So the limiting reagent is based on the molar ratio in our original balanced equation. So this tells us that there's a 1:3 ratio between nitrogen and hydrogen. So we just check 3 times 3,000 is still less than 11,900. So despite there being on paper, on weight, more nitrogen than there was hydrogen, we aren't, the nitrogen is going to run out first. It is the limiting reagent. So now we don't worry about hydrogen because it's not going to run out. Our theoretical yield, or how much we could produce, is based off 3,000 moles of nitrogen being present. Doesn't matter about anything else. So we take 3,000 moles of nitrogen. So for every 1 mole of nitrogen, there's 2 moles of NH3 being produced. So we times 3,000 by 2. So it gives us 6,000 moles. So theoretically, we can produce 6,000 moles of NH3. So before we went from grams to moles, now we need to go the other way, from moles to grams. So 6,000 moles. So again, back to some chemistry basics. How do we find the molar mass of NH3? Well, we find the total of the individual molar masses from the periodic table. So 2N. So we would have 6,000 so 14.01, which is N, plus 3 times the molar mass of, sorry, I was being lazy. So molar mass, we have to have the units. To get full marks, you have to have the units there. So this then will give us 102,000 grams. So if we go back to our original question, it says that we produced 68 kilograms, or 68,000 grams. So we divide 68,000 by 102,000, and that gives us our actual yield of 67%. So to break this down, first thing we do when you get the question about the Haber process, not if, when. You will create your balanced equation. You then determine the limiting reagent based on how many grams there are divided by the molar mass of whatever it is. So we then find out our limiting reagent. We work out our stoichiometric ratios, which is 1 to 3 to 2. So once we figured out that nitrogen is the limiting reagent, we don't worry about anything else. We don't worry about hydrogen after that. Completely useless. We don't need to know anything about it. So we say, well, for every 1 nitrogen, there's 2 ammonia produced. So we take 3,000, which is how much nitrogen we have, and we times it by 2, which gives us 6,000 moles of NH3. It can be produced from 84,000 grams of nitrogen. 6,000 moles equals 102 kilograms, or 102,000 grams. This is our theoretical yield. So if everything went perfectly, we would produce 102,000 grams. But it didn't, because we only produced 68,000. We divide this is the actual yield. and this is the theoretical. So we divide the actual by the theoretical, and we get the percentage yield, which is the actual theoretical yield. So that's how we do industrial chemistry. And that's stoichiometry. So if I have X amount of one thing, a different amount of another, how much of something can I produce? Oh, okay. I don't think there's anything in the industrial chemistry or anything else we need to. Yeah. So basically the idea is that most of these chemical processes are not 100% efficient, and they never will be. So I'm going to move on to the next. Now we're getting into the biological chemistry. So, in Unit 2, you would have learned about catalysts, inorganic catalysts. When we're looking at enzymes, they are what we call biocatalysts. I'm not going to spend a huge amount of time on them because I don't think there's going to be that much in the exam. So enzymes are biocatalysts. They speed up biological reactions, so they lower the activation energy. Like our magnetite in our Haber process, allows the reaction to happen at a lower energy level. If we were to look at graph, so the uncatalyzed reaction may go like this. So the energy required is on this axis here, and the progress of the reaction down here. So this is the uncatalyzed pathway. Here we have the enzyme catalyzed pathway. So you're getting the same thing for a lot lower energy. The activation energy is much lower when you add in an enzyme. Again, not going to go through too much, but enzymes are proteins. So they're catalysts, usually for one type of reaction. We have 3D structures in the proteins, which is the tertiary structure. And if we remember back to nucleic acids, they will be the bonds between the R chains of the amino acids. We have quaternary structure, which is made up of multiple polypeptide chains. Right, I'm going to go deep into biochemistry. Take a quick couple-minute break, get the rest of my notes in order, and then we'll smash through the last hour. A big part of this year's exam is going to be made up of polymers. Probably do a whole other session just on polymers, but this is just an exam study overview. So we're looking at polymers and how the structure of the polymer or how that influences the chemical properties, because the polymers are just organic molecules. So we change the functional groups attached and we change the polymers. So I'm going to stick with plastics. We'll do another one on proteins and carbohydrates as well. So we have, colloquially, polymers are known as plastics. And we use them because they're lightweight, because they're sturdy, they don't break down. The term plastic is not actually, it's not actually a material, it's just the property of the materials. So we take monomers. So we have monomers being one. We add them together and we get polymer. Polymer meaning many. Very simple. So normally plastics are made up of ethylene, ethane. So we have then we have another one. So they join to become a polyethene segment. Okay. So two monomers of ethene are reacted together to form polyethylene, or polyethylene. So some of the things you might be aware of: polyethylene, this type of plastic; polypropylene, polypropylene, like vinyl floors. We have polytetrafluoroethane, which is your Teflon. So polymer just refers to many monomers attached together. So we have, and they used to print it on the plastic. I don't think they do it anymore. You look at old Tupperware, it'll have either LDPE or HDPE. So LD being low density polyethylene. It's made under high pressure and high temperature. Let's do LDPE for now. Made under high temperature and high pressure. It's quick, it's cheap, and it's easy. What happens is, instead of it being a nice straight molecule, you get all these chains coming off it. So low density refers to how tightly they are packed. So they will be packed like this. So they're not packed tightly together. Now, remember back to what we did with the boiling point. If the molecule has chains, the intermolecular forces between the molecules are going to be low. So low density polyethylene is weak, it's brittle, and has a low boiling and melting point. It's still only dispersion forces, because we know from Unit 3 that the dispersion forces are weak. So soft plastics, squeezy water bottles, all have this LDP. They are cheap to produce, they're quick, they're nasty. They don't have a very crystalline structure, low melting point, they're soft, they're low density, meaning that you can crush them up and break them. And they don't conduct electricity. Now, plastic generally doesn't conduct electricity, and especially when it's LDP. Then we have this cool new one that came out a little while ago, and it's high density. It's called high density. polyethylene. So high pressure, high density, sorry. And it's produced using a really low pressure and low temperature, using the Ziegler-Natta catalyst. So we use a low temperature and low pressure, which creates straight chains. They might have a few little branches coming off them, but they're really quite small. So the high density means they pack in much closer together than with the low density. So they are hard. So if we were to look at an example of HDPE, you would have like this cup. It's rigid, it's hard. It's not old enough to still say HDPE. But these are things like components on cars, computers, things that are plastic, are hard plastic. They have a really high melting point because the intermolecular forces are higher. And almost, they become like a crystalline structure. So we know what a crystalline structure, it is incredibly ordered. So when we have ordered bonds, like in salt, we get a crystal structure. This means that we get plastic that can conduct electricity. It's really, really hard. It has a really high melting point. And now this has led to the creation of what we call ultra-high molecular weight polyethylene. So they've made the backbone millions and millions and millions of carbon atoms long. Carbon backbone is millions of carbon atoms long. The longer they make it, the higher the intermolecular forces, so the stronger it will be. Now, they can use ultra-high molecular weight polyethylene to make bulletproof vests. So we're making bulletproof vests out of plastic. Helmets. I'm making unbreakable parts of cars. You can use ultra-high molecular weight polyethylene to make boats that can basically crash into things and they just bounce off. So the molecular weight refers to the increasing carbon chain length. So we know that these hydrocarbons, which is what the plastics are made out of, has weak dispersion forces. But if we put so many carbon atoms on there that it doesn't matter, we just make up for it by making it millions and millions and millions and millions of carbon atoms. Then we can produce plastic that is stronger than a lot of metals. So if we go back to this branching, we can control the branching through the manufacturing process. We want cheap, nasty, soft plastic. We make it in really high pressure, high temperature environments. We make HDPE plastic in nice, subtle environment with a catalyst. So when we're looking at HDPE, it basically becomes a crystalline structure. So we can use it for pipes, buckets, fuel tanks. So it's so strong and resistant to corrosion that we can put petrol in. So if we look at the arrangement of the side chains so if we look at, we're never going to have no chains. It's not going to happen. We're dealing with a random reaction. We can control the conditions to an extent, but we still will have branching, but we can control what happens with the branch. So we have 3 different ways that we can affect the properties of plastic. So, sorry, not plastic, polymers. So we have isotactic or isotatic, atatic, and syndio. And it refers to the arrangement of the side chains and where those side chains line up. So isotactic, sorry, it is tactic, not tactic. Isotactic all of the side chains that occur on the same side. So when another isotactic polymer comes along, they can get really close to it. So the closer they are together, the stronger the dispersion forces, and the higher the order, or the more ordered it is. So these just keep stacking on top of each other. You get crystalline regions. So the attractive forces between the molecules is really, really high. We make baby bottles out of them. So we need baby bottles to be strong, to not break down. And the last thing you want to have on plastic is where it gets scored, because if you have a baby bottle that's got scoring on it from being heated up all the time, then it's going to trap bacteria. Australian banknotes are made of this isotactic plastic, thermal underwear. So the atactic, you have random distribution. So then on the next chain, it'll be like this. So there's no order to them. So there's going to be no crystalline region. So this is for like just your everyday water bottles that you buy. You pay a fortune for. The syndiotactic is the one where we're starting to look, well, this will display almost metallic properties. So the side groups are on regularly alternating sides. The next molecule that comes along will have this thing. So this way is almost perfectly crystalline. It will conduct electricity. It's relatively new. The idea is that we can replace a lot of the metals that we use with this syndiotactic polymers. So there's some really cool examples. I'm just going to grab a different tissue for wiping the board off because I'm covered in black. So there is some of these polymers in use already that have some cool uses. The most interesting one, I think, is superglue. So superglue polymerizes when it comes in contact with the air. So all of these polymers are based on the polyethylene backbone. So polypropylene, so this is just plastic. We replace all of these with fluorine. And we have Teflon. So Teflon is non-stick. You have to heat it well above 350 degrees to break it down. So what this means is that, so fluorine is the most reactive element. So nothing is going to come along and knock the fluorine off. Fluorine is so non-stick that it takes about a week of breaking down a pan. So scratching it, applying a little bit of Teflon, scratching it again. It takes about a week to make a Teflon coated pan because it's such a hard, it doesn't stick to anything because the fluorine will never get knocked off here because it's the most reactive. Okay, so let's look at, if we add 2 chlorine molecules. We have intruder. If we had 2 chlorine molecules, we have dichloroethene, we get cling film. So we can test and change the property of these polymers by taking off the end. Remember back to our substitution reactions and all that fun stuff. We can see what's going on here. So most of our synthetic fibers actually have a nitrile or a cyanide group attached. So these are our, so they call it propene nitrile, very creative name. But it has this nitrile group attached, and that is what makes most of our synthetic fibers. So if we add kind of the bane of the existence on the world at the moment is styrene or phenylethene. So what we've done is we've inadvertently created something that will never break down. So my awesome drawing of a phenol group. So that is styrene. So why is that bad? Because this ring here absorbs all the sunlight, and normally plastic will break down over a period of time because the sunlight's breaking the bonds and it will eventually disappear. But when you add a phenol, a benzene ring, fortunately that will absorb all the sunlight and the molecule won't break down. There's a big push to not have any polystyrene being produced or used anymore because it's not great for the environment. Let's do one more. This is the most interesting one, I think. Is superglue. So superglue is a liquid inside, as most of us know. So when superglue comes into contact with the air or with water, which is in the air or on the skin or whatever you're putting it on, you shouldn't put it on your skin. but it creates a polymer in contact with water. So inside the superglue tube, it's not actually superglue. It's only superglue when you bring in contact with water. But the idea is, we remember back to our reaction pathways. We start with ethene, and we just play with what's attached to the outside. We can attach halogens. We can attach. We can turn the halogen into the amine. We can turn the halogen into the nitrile group. So with an understanding of all that, we can understand how to create new polymers. Polymers can be formed through a condensation reaction, which is the reaction where you join them together. So methanol or water is usually the byproduct. So the most important property of polymers is the crystallinity. The higher the crystallinity, the stronger and higher the intermolecular forces will be. So perspex, which is clear plastic, is very crystalline. Okay, well, let's move on to what we got left. Might just do chemical synthesis. And that will, so we're just going to finish on chemical synthesis. I'm going to have to run another session, maybe of 2 hours length, maybe 2 1-hour sessions to finish this. I thought I could get through it all in 4 hours, but I took my time and got the organic chemical. It's the most important. So, chemical synthesis. Again, another new thing that I've taught for this year. So, this ties in with the organic chemistry. How can I produce something from something else? So there's different pathways. So we start with what we call a retrosynthetic pathway. How do I produce something? So I want to create this target molecule, my red and black. So I know what the target molecule is, but I don't know what the reactants are. So I break it up. So this is AB. I then break it back up into A plus B. And then I figure out actually what is required. What happens when I break that molecule up? What are the bits of it? And then we can use that in order to figure out how to create the target molecule by breaking it up into its constituent pieces. So let's look at some simple reaction pathways. The creation of an ester. So we start with an ester. Sorry, we start with an let's stick with alkane. So this is that the previous thing we looked at with organic chem, just taking it up a notch. So we take ethane. Again, this is something you will need to know. We then react it with chlorine. So we take our alkane, then we turn it into, sorry, it would be, if it was ethane, it would be. So we react it with chlorine, it becomes a haloalkane, or chloroethane. So it becomes so we've just replaced, through a substitution reaction, we've replaced the hydrogen of ethane with the chlorine. Now, we know we can create ethanol from chloroethane or haloalkane by reacting it with sodium hydroxide. So we react the haloalkane with sodium hydroxide. This allows us to produce ethanol. So instead of the chlorine being there, we're replacing it with OH. So now we can make ethanoic acid from ethanol. So we react ethanol and hydrogen. So then we end up with ethanoic acid. We can then turn the ethanoic acid so we add ROH as well as H2. SO4. This then produces so now we're putting all that stuff we learned together into one diagram. So alkyl ethanoate so that's a reaction pathway that we can use to produce an ester or anything along this pathway. Picture my beautiful outline. So that's one of the reaction pathways. So that's a simple reaction pathway, believe it or not. And it's definitely one that you'll need to know. So I think I might finish on this. So, because I think everyone's brain is going to explode, including mine. So I want to synthesize ethyl propanoate. So I want to make ethyl propanoate. What I need to do is produce an alcohol first. So I want to produce ethyl propanoate. So I start with ethene. So I need to make an alcohol first. So I take my ethene. And if we remember how to make ethanol from an ethene, easy way, we just add water and H3PO4, which produces ethanol. So we're just going back to those reactions that we looked at earlier. So we go from ethylene or ethene directly to ethanol. So we then need to make carboxylic acid. So we need to make propanoic acid. So we take propane. So this is a completely separate reaction. I'm definitely going to finish on this, I think. So we make the alcohol, then we make a carboxylic acid. I think I'm just going to do the full reaction, shortened reaction pathway. So we make the alcohol, we also need to make a carboxylic acid. I'm going to do a slightly different way. So we have to make two separate molecules. We have to make ethanol and propanoic acid. So propanoate is what we call an ester, or O8 is an ester. So we make alcohol plus carboxylic acid. So the very first part of this is start with ethene. We then create using water and H3PO4, we produce ethanol. CH3, CH2, OH, which is ethanol. So we just need that part of the reaction is done. Get down on my hands and knees. Let's try and write neatly. So we start with propane, which is so we react propane with chlorine to produce 1 chloropropane. So we have CH3, CH2, CH2, and Cl. Or so propane this is in the presence of UV light. So we mix propane, chlorine, it makes 1 chloropropane. So chlorine is attached to the first carbon with a propane backbone. We then react this with sodium hydroxide because we know that will produce an alcohol. So this part of Year 12 chemistry brings absolutely everything you've ever learned together. So we then react with that and we get propane 1-ol. So we produce an alcohol. So CH3, CH2, CH2, or propane 1-ol attached to the first carbon. It's only attached to one, directly to one carbon. We then react that, and this is all, I will include all of those slides in the pack that I send out with this. We reacted with Cr2O7 2- and H+, and we produce the carboxylic acid, or propanoic acid in this case. So this is propanoic acid. Still propane 1-ol, I'm just doing color coding. Propanoic acid. Which is a carboxylic acid. So we react ethanol, propanoic acid, in the presence of hydrogen sulfate. And we get, so going out of my color coding. we get CH3 C double O CH 2 CH3, which is ethyl propanoate. So this is ethyl. Because there's 3 carbons in that way. Okay, I think I'm gonna end it there. So I'm gonna do a couple more probably recordings or maybe live sessions as well, and we'll go through acids and bases, redox reactions in a lot more detail. We just got through close to a year's work in 4 hours. So if your brain's feeling a bit fried after watching that, you're not alone. So thank you for watching, and I'll put out the details about the additional session.